Hey guys, welcome back to Explore Electronics. In this video, let's see the solutions to the model question paper of the subject VLSI Design and Testing with the code 21EC63. The first question is, with necessary circuit diagram, explain the operation of tri-state inverter and realize 2:1 mux using tri-state inverter. Here the tri-state inverter is that it is a normal inverter with a control signal. When this control signal is 0, the inverter output will be tri-stated to Z. When the control signal is 1, this will be operate as a normal inverter. You can see the truth table. When enable is equal to 0, irrespective of the input, output will be Z. And when enable is equal to 1, when input is 0, output will be inverted to 1. And input is 1, output will be inverted to 0. You can see the first circuit here. This will be having 4 transistors, 2 P transistors and 2 N transistor network connected in series. It is a tri-state inverter now. So enable and enable bar will be given to 1 N transistor and 1 P transistor. When this enable becomes 1, you can see when enable is equal to 1 here, the 2 transistors will be on, both N transistor and P transistor. In between are 1, and this will be act as a normal inverter. When A is 1, A bar will be generated as output as 0. So when enable is equal to 0, what is the case? The in between 2 transistors will be off, means output will not be connected to VDD as well as it is not connected to ground also. That's why there is no direct connection for the output terminal. So we say the output will be tri-stated to Z. There is no path to discharge as well as there is no path to charge. That's why the output will be tri-stated to Z. Now let us come to the second part of the question, that is we need to realize 2:1 mux using tri-state inverter. The 2:1 mux says there will be a single select line and 2 inputs. We are taking it as AB and select line is S. When S is equal to 0, A should be selected as output. When S is equal to 1, B will be our output. That's why Y is equal to A into S bar plus B into S is the expression for this 2:1 mux. So it requires 2 tri-state inverters here, and the control signal here in place of enable we are using S. How we are supposed to provide the inputs in the sense, since A, B are the inputs here and these are the inverters, we are providing A bar and B bar, so that we will be getting A over here and B over here. And the control signals are given such a way that when S bar is 1, A has to be the output. That's why S bar will be given to the N transistor. It means here S bar in the sense it is 0. When 0 is my S is equal to 0, A will be the output. That means S bar is equal to 1, A will be the output. Similarly here, when S is equal to 1, B will be the output. So this is the arrangement giving the 2:1 mux functionality. This gives A into S bar plus B into S functionality at the output. Then the second question is, realize CMOS gate for the following function, Y is equal to A into B plus C plus DE whole bar. So the related video is available in the playlist of VLSI design in my channel. You can see that some complex expression are taken and how to write the circuit using CMOS logic is explained. So coming to the question, here A into B plus C plus DE is given. So B plus C we need to realize first. So B plus C in the pull down network will be in parallel since it is B plus C, and it will be in series with A into B plus C. That's why A will be in series with B and C. And for this network A into B plus C, we will be having plus DE, means parallelly we need to connect 2 series transistors with the gate input DE. So this pull down network you need to write first, and by looking at the pull down network you need to write the pull up network by converting the series connections into parallel and parallel connections into series. Then we are going to get the output Y as A into B plus C plus D. If you have any doubt in making the connections, you visit this video. The video will be having many complex circuits designed. You will come to know how actually the logic will be. Then the next question is, implement a D flip-flop using transmission gate and explain its operation with necessary timing diagram. Here is the detailed explanation given. So the D flip-flop circuit is this. You can see there are 4 transmission gates are required. So the first half of the circuit here given as blue color will be act as the negative level switch or the latch, and the second half means the orange colors circuit indicating the positive level latch. So these two latches combiningly making the circuit of D flip-flop. When clock is equal to low, you can see here T1, T4 is on. It means this T1 and T4 transmission gates are on. What happens when the clock is low here? This transmission gate will be on. The D will be passed to the inverter. D will be inverted. Again, we will be having one more inverter. This will be again making D as a normal true value. And here this transmission gate is off, so that it will be in this stage. When the next positive edge comes, what happens? So next positive edge means clock become high. Clock is low here, we are giving the D, and when clock becomes high in the next subsequent time, what happens? T2, T3 will be on. T2 is this and T3 is this. The value of D will be present over here. Now this transmission gate is off, so that we are not taking the value of D. The previous value what we have taken over here will be processed, and since this T2 transmission gate is on, it will move to the next stage. The next stage transmission gate T3 is also on, so that we can invert it and send to the output Q. So this is how we are going to get the same value of D in Q. You can see the path over here, 4, 1, 2, 5, 6, and then it will reach Q. You can read this, you will come to know the detailed explanation. This much of answer is required for the 7 marks. Then comes the second question, that is in module 1, the choice question. Here they have asked CMOS inverter circuit diagram, and with the help of its transfer characteristics, we need to explain the different regions of operation and derive the Vout equation for region C. So for this, first you need to write the circuit diagram of CMOS inverter. This requires one P transistor and one N transistor, and you need to mention clearly the drain source as well as gate. This is what the circuit is, and you need to write the transfer characteristics. Vout in y-axis and Vin in x-axis. When Vin is 0, the maximum output we are going to get from the inverter. That's why Vout is maximum. Maximum output in the sense it is VDD. Why? Because when Vin is equal to 0, transistor P is on and VDD will be the output. That's why the maximum output VDD we are going to get. As we start applying Vin will be increased. What happens? The output will be keep on decreasing. Why? Because when Vin, the input reaches the threshold voltage of the N transistor, initially N transistor will be off. Now it will be started to turn on. When it started to turn on, there is a discharge happens through this path from the output terminal. That's why the output will be keep on reducing, and finally it will become 0 when the input reaches the maximum value VDD. So that's why it is a smooth curve like this, and we can divide that as region A, B, C, D and E. And these regions are divided in such a way that here up to this stage N transistor will be off. From this stage onwards N transistor will be on, and then at region C both the transistor will be in the saturation region, means exactly at the half of the input given. And later on again VDD minus VTP is the threshold point of the P transistor. From here onwards P transistor will be off. So the 5 regions indicating the different levels of the transistors P as well as N. You can see the conditions over here, and also the P transistor and the N transistor regions of operation. So depending on this, we need to explain how actually the transistors will behave and the output will be generated in, and the curve will be in each and every regions. You can see the video which is available in detail. I have explained the CMOS inverter and its characteristics. It is there in VLSI design playlist. And coming to the second part of the question, that is derive the Vout equation in region C. It is very easy. At region C, both the transistors will be in saturation. It means both transistors are on. Both transistors are on in the sense current will be equal. And we say Vin will be at the half of the maximum voltage, and also Vout will be at the half of the voltage. VDD by 2 is the output. And the derivation is given over here. You can see IDSP is minus IDSN. Why? Because drain to source current we are going to take. In terms of drain to source, if we take, this is the current direction, means VDD to Vout, the current will flow. In P transistor it is shown as reversed. That's why we need to take it as minus. But N transistor flow will be Vout to VSS. So it is taken as minus, and this is the expression for current in the P transistor when it is in saturation region. This is the expression for the N transistor current in saturation region. And if we take these two and equate, any of these two are equal with negative sign, we will be getting the expression for Vin. This Vin will be having beta N, beta P values. If you consider beta N, beta P are same, and also the threshold voltage of the two transistors magnitudes are same, then we will come to know that Vin will be equal to 0.5 into VDD, means that is exactly half of the VDD. And at that stage, you can see this implies the changeover between the logic levels is symmetrically deposed about at the point where VDD or half of the VDD will be Vout. So we need to take Vin and Vout as half of the VDD. That is exactly the point where we consider it as region 3. This is how you can derive, or you can directly write also. Then comes the second question in the choice, that is derive the equation for drain current of a MOSFET in non-saturated and saturated regions of operation. This is a very important question, repeatedly asked, and also the MOSFET operation can be asked. So to derive the expression for MOSFET, we need to take the charge into consideration and also the time with respect to the charge flow. So here the drain to source current will be equal to charge induced in the channel. This is the channel between source and the drain end, and divided by charge in the channel divided by electron transit time. So here the electron transit time will be calculated first. It will be equal to length by velocity. The transit time T is equal to length by velocity V. So here velocity will be taken as mu into EDS, that is electric field into electron mobility. Here, since it is a N transistor, we need to take it as mobility of electrons. And here EDS, electric field, will be equal to the voltage across the channel, that is from drain to source, that is VDS, divided by length of the channel, that is L. So if we substitute EDS over here, the velocity will be equal to mu into VDS divided by L. And then substituting this in the expression of TSD, that is transit time, it will be L square divided by mu into VDS. Now we got the denominator in my current expression. Now we need to calculate QC. What is QC here? QC is the charge induced in the channel. So QC will be equal to, if you take the charge per unit area in the sense 1 by 1, it is Eg into epsilon ins epsilon naught. Here Eg is the average electric field in that area, into relative permittivity of the insulation between the gate and channel, since we have a SiO2 layer over here, and epsilon naught is the permittivity of the free space. Now we are calculating for the complete length of the channel, so we need to take W into L, means width of the channel as well as length of the channel. That's why W into L is multiplied here. So if you take this, and we need to place Eg over here. Eg in the sense average electric field. If you calculate, again we voltage divided by the depth. Here the depth is taken, depth of the channel is taken. Why? Because here gate to channel we need to consider. Depth of the SiO2 layer, this is D, we need to consider while calculating the electric field between gate and channel. This is D. That's why it is D. Here we have taken the electric field EDS as VDS, the voltage, divided by length of the channel. Here we are taken voltage between the gate and the channel with respect to drain, and D is the sorry, not drain, it is thickness D. And now we are going to get QC is this, and combining these two, QC and TSD, that is transit time, we are going to arrive with this expression. And solving that expression, replacing this constants with K is equal to epsilon ins epsilon naught mu divided by D, and we are replacing that again with beta. We will be arriving with the non-saturation current equation as IDS is equal to beta into VGS minus VT into VDS minus VDS square divided by 2. This is the expression for non-saturation region. You can see here in the non-saturation region, the current will be dependent on VDS as well as VGS. Now comes the saturation region. When saturation region begins, what we say the condition is the drain to source voltage will be equal to VGS minus VT or greater. So we need to replace this VDS will be replaced by VGS minus VT. Here also VDS square will be replaced by VGS minus VT. Then we will be getting the expression for saturation region. The same expression taken as VDS in place of VDS, we need to take VGS minus VT. So we will be getting IDS is equal to K into W by L, VGS minus VT whole square by 2. This is the expression for saturation region current. So these two they have asked to derive. This is for 6 marks. Then comes the first module last question. Compute the output voltage V out in a pass transistor circuit shown in the figure 1. This is the circuit they have given. Here the thing is that, remember this, for NMOS pass transistor, the condition is that the gate voltage should be greater than VT to turn on. That is the basic criteria. And then if the drain voltage is less than VGS minus VT or VG minus VT, what we say, the source voltage will be same as drain voltage. Suppose if the drain voltage is greater than VGS minus VT, then we say the source voltage will be VG minus VT, means the output will be degraded. Suppose if the 4 volt is given over here and 5 volt is given over here, gate voltage is more than the drain voltage. Even if we take the drain voltage as 4 volts and if we calculate VG minus VT, VG is 5 volts and the threshold voltage of this will be somewhere 0.7 volts. If we minus 0.7 volts from 5 volts, that is again more than 4, it is 4.3. That's why gate voltage, gate and threshold voltage, if we subtract, it is 4.3, that is greater than the drain voltage, that is 4 volts. That's why the source voltage will be same as drain voltage, we are taking it as 4 volts. Similarly here, the other way is that simply see the drain voltage and the gate voltage is more than 1 volt difference, we can calculate it like that and we can say the same voltage will be passed. Otherwise we need to subtract this 4 volts with a threshold voltage of 0.7 and we need to take 3.3 as the output. Because of the gate voltage is more here compared to drain voltage, we are taking the same value. These two conditions we need to remember while solving these pass transistor logics, while one pass transistor is driving the other pass transistor. The first module B plus C plus DE whole bar. So this gives the correct result. Module 2, the first question, explain various steps in CMOS N-well process with necessary diagrams. They have asked to write the N-well process and with diagrams. But here the P-well process is shown. You need to convert this P-well process into N-well process in your answer. So the thing is, in the parent N substrate, P-well is created here. So for N-well, what we need to do, in the parent P substrate, we need to create the N-well. So here the change what we need to do is that in place of N, we need to write P substrate and the indications correspond to that. And in place of P-well, we need to create N-well. So when we create the N-well, we need to diffuse the P diffusion in that place. That's why what we need to do, take this N-well at left side, create the N-well at the left side and keeping the N substrate as it is. And then the polysilicon deposition will be same. Your N-well will be at the left side here. There will be no well at the right side. And then we need to diffuse P. Why? Because in the N-well, we need to diffuse P diffusion we need to make so that it will create a P transistor. And at the right side, for the N diffusion, we need to do the N diffusion in P substrate. So parent P substrate will be there. In that you are going to diffuse N. So this step is also same. And the next thing is that you need to write this diagram. Here the cross-sectional view of N-well process. You can see the well is at the left side here and you have created two P diffusions that will be act as a P transistor, and at the right side you have two N diffusions that will be for the N transistor, and N transistor source will be connected to ground. Here it is VSS, and P transistor source will be connected to VDD, and two drains are taken for output and gate are connected for input. So this is the N-well CMOS inverter you are supposed to write, and where the N-well is at the left side. Here also I have shown the P-well process, replace that by N-well process. I hope you have understood. Then comes the second question here. With need diagrams, explain lambda based design rules for wires, contact cuts and transistors. First let me take wires here. Here we have diffusions and polysilicon and metals. These are the wires we can consider. So the rule, lambda based design rule says, for N diffusion, the minimum width of the N diffusion should be 2 lambda and P diffusion also should be 2 lambda. And the difference, the spacing between the two N diffusions should be 3 lambda and spacing between the two P diffusions should be 3 lambda. And if any other polysilicon layer comes in between the P diffusion or N diffusion, the spacing should be 1 lambda. And for polysilicon also, the width, minimum width we need to maintain as 2 lambda and the spacing between those two is 2 lambda. For diffusions it is 3 lambda spacing and for polysilicon it is 2 lambda spacing, and to diffusion to polysilicon it is 1 lambda spacing. You need to write this in the same way and explain what I have explained so far. For the metals, we have two types of metals. One, metal 1 we call it as, and we represent that with a straight line, and metal 2 with a horizontal line. Metal 1 will be having minimum width of 3 lambda and spacing between the two metal 1 layers will be 3 lambda itself. For the metal 2, we need to have 4 lambda as width and spacing as 4 lambda. This is for wires. Wire in the sense it is diffusion, polysilicon and metals. Coming to transistors now. Here NMOS, PMOS and depletion type transistor is shown. The polysilicon crosses the diffusion will be a transistor. Means this one polysilicon layer and this diffusion layer crosses like this, then it will be a transistor. So as we know, diffusion will be having 2 lambda width and polysilicon is also having 2 lambda width. So here the vertical and horizontal lines what we take as diffusion and polysilicon also having 2 lambdas. That's why the crossing will be indicated over here at the center as a channel. This channel will also be with the size 2 lambda cross 2 lambda. That is what the meaning is. Similarly, for the PMOS transistor, you need to take this P diffusion representation and horizontally taking P diffusion and vertically taking polysilicon. And if it is a depletion transistor, we know that in the depletion transistor, the channel will be already created. To show that, here is the dashed box indicating, this will be called as a implant, means that is the channel representation in a depletion region. It is already created. The channel is here itself, but it is already created, will be represented with a dotted box like this. It will be with the size 6 lambda cross 6 lambda in our layout. And this is for the transistors. Coming to contact cuts. Contact cut in the sense, when actually the contact cut comes into picture, when metal contacted with a diffusion like this, or polysilicon contacted with a metal and polysilicon contacted with a diffusion, means different two types of layers are connected, we call it as a contact cut. Here you can see metal 1 and a polysilicon connected. So 3 lambda will be for the metal and 2 lambda representation for the polysilicon, and the two has to be connected with a contact cut like this. It will be having 4 lambda cross 4 lambda size. The metal as well as polysilicon representation will be there here. It is having 4 lambda horizontally, 4 lambda vertically, and in center we will be having a cut, means cut in the sense the connection we need to show darkly. That dark centering will be for 2 lambda cross 2 lambda. That is what the contact cut rule is. Similarly, if you come vertically and horizontally, you need to show like this, and if it is connected vertically horizontally like this, you need to show like this. And if you have two contacts one after the other, the difference between the contact cut inside will be 2 lambda. And you can see here the other diagrams also showing, this is via connecting between metal 1 to metal 2. When the metals are connecting, we call it as a via. This via will also be 4 cross 4, since metal 2 and metal 1s are connecting. Metal 2 is 4 lambda, metal 1 is 3 lambda. but the contact is for 4 cross 4. This is what for the wires, contact cuts as well as transistors. This much of diagrams and also minimum explanation is required here for 6 marks. Then comes draw the stick diagram for the function y is equal to a into b into c plus d whole bar. So for this is the circuit. In the pull down network you can see a into b into c is there. So to get that we need to connect the 3 transistors with gate inputs a, b, c in series, and d will be plus d, so we need to connect it in parallel. And in the pull up we need to connect a, b, c in parallel series with d transistor, and at the junction of pull up and pull down networks we need to take the output y, and pull up network will be connected to VDD and pull down network will be connected to ground. For this let us write the stick diagram. So to write the stick diagram for this, first what we need to do, we need to take VDD as a metal and also we need to take ground. First write these 2 lines as VDD and ground. After writing VDD and ground, what we need to do, we need to write these 4 transistors and these 4 transistors. So for that let me take this red color indication for the gate of the transistor, and we can place 4 transistors over here, and horizontally I am taking source and drain of the transistors. These are the P transistors representing the diffusion with blue color here, and in your exam you can write without any color representation, that is not required. So now here we have 4 PMOS transistors and I have taken 4 NMOS transistors. NMOS transistor diffusion, that means source drains, are represented with green mark, and the red indication that is for gates, and blue indication for the PMOS diffusion. So now let us name these source, gate as well as drain first. So here since we have taken the output from here, this is our drain of the transistor. Okay, this is our drain. Similarly for A transistor of the pull down, here we need to take the drain, and also here it is drain. First we need to mark which are all the drains. Anyhow we know where actually we are going to take the output. And similarly for the B transistor, this is my source, and also for the A transistor this is my source. And then comes the remaining, okay, let me mention this as source of the C transistor, this is source, and for the D transistor also this is source. Whichever the terminals connected to ground and VDD will be source, and whichever the terminals connected to output are drains. Now it is easy to represent the other terminals, since this is a source of the C transistor, this is the drain, and similarly for the B transistor this is drain. Similarly for the A transistor, the remaining terminal, this is drain. And here also for the below transistors, since drain is already taken, this is source, and here for the C transistor the other end is source already, then this become drain. Now we have a choice that we can take source and drain of the transistor B however we want. Now let me write the stick diagram. So now you can see this is the complete stick diagram for the expression given. I have mentioned the terminals here clearly, where is source, where is drain, and according to that you need to make a connection, and where the 2 layers are connecting. See here the metal is connecting to diffusion in the source connections. That's why I need to connect VDD with a dark indication like this. This represents a connection. For the transistors we will be not mentioning that connection. Why? Because if we mention the connection, that becomes a contact. It is not a contact, it is a crossing between diffusion and a polysilicon. So for transistors, not supposed to mention the connections, and whenever the 2 layers are connected for ground as well as for the output and also for the VDD, we need to show the connections like this. This is the stick diagram for the expression given A into B into C plus D whole bar. Now the next question is, construct necessary equivalent circuits using RC delay model to compute the propagation delay of 3 input NAND gate. 3 input NAND gate structure you need to write first. So for the 3 input NAND gate, you need to write the capacitance and resistance parameters. So by taking the worst case output, falling transition, and output pull down through the 3 series NMOS transistors. The 3 transistors are connected in series in the pull down network. 3 transistors P transistors are connected in parallel in the NAND gate. So we need to take the worst case output falling transition by taking output will be pulled down through the 3 series transistors whenever they are on. By taking the output falling means output will be 0. When actually the output of the NAND gate will be 0? When all the 3 gate inputs are 1. In that case, the 3 pull down transistors will be on and the pull up transistors will be off. And then taking the worst case of rising transition in the sense at least 2 PMOS transistors will be off, at least 1 transistor will be on. That can be considered as a rising transaction. According to that, upper 2 NMOS transistors are still on, we can say, and bottom one is off. And the series capacitance of upper 2 NMOS must also be discharged during the falling transactions in the worst case. So by considering these cases, we need to write the RC equivalent circuit when the output is falling like this, and also RC equivalent circuit when the output is rising by taking the worst cases. So this is what the answer for RC delay model to compute the propagation delay of the 3 input NAND gate. You can see here the complete transistors capacitance are shown in this diagram. And then the next question is make use of the necessary waveforms to define the following terms: propagation delay, contamination delay, rise time delay, fall time delay, and edge rate. It is the maximum time from the input crossing 50% to the output crossing 50%. You can see here this is the input signal, this is the output signal. As we know in the CMOS circuits, when input rises, output will be falling down. We need to consider the time at which input is crossing 50% of the value, and we need to take the output which is crossing 50% below. That time will be called as propagation delay. You can see this is the propagation delay when the output is falling, and similarly this is the propagation delay when the output is rising, we can say. Then we have contamination delay. Contamination delay time is that minimum time from the input crossing 50% to the output crossing 50%. Here we need to take the minimum time, and the propagation delay says it is the maximum time. Then what is rise time? Rise time is that time for the waveform to rise from 20% of the value to the 80% of the value. From here you can see the rise time from 20% of the total output to the 80% of the total output. Suppose if you take 1 volt as the maximum value, it will reach 0.2 volts to 0.8 volts. What is the time it is going to take to reach that value is rise time. Similarly, falling from 0.8 to 0.2 will be taken as fall time. And the next thing is edge rate. Edge rate in the sense it is adding the rise time as well as fall time and taking the average of that divided by 2 is edge rate. Then we have the next question: make use of necessary circuit diagram to compute the logical effort of the following gates. Here 2 input NOR gate need to be explained and 3 input NAND gate need to be explained. In the diagram you can see this is an inverter. We need to take the inverter as reference. Why? Because the logical effort says it is the ratio of input capacitance of the gate to the input capacitance of an inverter that can deliver the same output current. So we need to take the inverter as reference. So better to write the inverter also in your answer. So here Cin is equal to C3, G is equal to 3 by 3. In the denominator we need to take the inverter capacitance into consideration. Similarly, for the 3 input NOR gate is shown over here. 3 input NAND gate. In the 3 input NAND gate, 3 series transistors and 3 parallel transistors. So Cin is 5 here. Why? Because 3 plus 2 is 5, and we need to divide the capacitance of the inverter consideration, that is 3. 5 divided by 3 is the logical effort for the 3 input NAND gate. Here 3 input NOR gate is shown. It is 6 plus 1, 7. For the single input I am telling, 7 by 3 for the 3 input NOR gate. In the question they have asked 2 input NOR gate. You can see in the table for the NOR gate of 2 input it will be 5 by 3. Why? Because here we will be having 2 transistors in pull up and 2 transistors in pull down, since it is a 2 input NOR gate. Here the 3 input is shown. Just convert this into 2 input NOR gate and write. And it is 5 divided by 3. Here it is 7 divided by 3. And that is what the answer for the question for computing the logical effort. Make use of necessary circuit diagram. Explain the operation of 3 transistor DRAM cell. So the question is on DRAM. We need to explain the 3 transistor based DRAM cell. So here is the circuit. In this circuit, you can see there is a NMOS depletion transistor which will be work as pull-up transistor. In the pull-down, we will be having three transistors T1, T2 and T3. These three transistors are responsible for storing the data and to retrieve the data. This bus is the output signal of this CMOS network. This bus will carry the data which we want to write or read. And here T1, T2, T3 are connected in such a way that T1 gate will be connected to write signal and T3 will be connected to read signal. And T2 gate is connected to the output of this T1 transistor, where the gate capacitance of T2 will hold the charge. Means the memory storage device here is basically T2. Now let us understand the write operation. In this case, what we need to do, this WR corresponds to write control signal and RD corresponds to read control signal. In the write operation, this WR need to be make 1 and RD make RD to be 0. When RD is equal to 1, we can read the data. When WR is equal to 1, we can write the data. Now we are making this WR is equal to 1. Means it will be turning on the transistor T1. At the time RD should be 0, so that T3 will be off. And the value present in bus is the bit we are supposed to write. This bit will be taken into T2 through T1. Remember, we have made WR is equal to 1. It is turning on the transistor T1. Whatever the data present in bus will pass to the gate of T2. Now T2 gate capacitance will be charged, and that will be the data which is going to store over here. This is the write operation. And later we are making WR is also 0 and RD is equal to 0. In that case, what happens? There is no direct connection established for T2 in any manner. So T2 will hold the charge. Let us understand the read operation now. So now in the read operation, what happens? WR will be kept 0 and RD will be kept is equal to 1. Means we are making read. That's why RD is equal to 1. And remember, we have stored in the gate capacitance of T2, that is the value 1. Means T2 will be on now. Because of RD is equal to 1, T3 is also 1. So in this case, what happens? This bus will be getting a direct connection established for a ground signal. So that's why bus will be pulled to 0. Means we have stored 1 over here. That's why T2 is on and T3 is on because we are reading the data, and bus will be getting direct connection to ground and bus will be pulled to 0. If we get 0 from the bus, 0 at the bus, it means we are reading 1. It is reverse. Similarly, if 0 is stored over here and we are trying to read the data, what happens? RD is 1, T3 is on, and if 0 is stored, T2 will be off. Means bus will not get the direct connection to ground. Because of that, bus will be having some positive value. Because of some positive value present in the bus, sense amplifier will detect that and it will treat that as logic 1. This is how the write and read operation can be done using 3 transistors in a DRAM cell. The next one is SRAM cell. The question will be on working of operation of a full CMOS SRAM cell with necessary topology. Here for CMOS cell, you can write 4 transistor cell also and you can write 6 transistor cell also. Better to write both, but here I have given only 6 transistor cell. 4 transistor cell also looks similar. You can understand this and go back and learn 4 transistor cell if you want. Here we have 2 bit lines. You can see bit and bit bar. If bit is equal to 1, bit bar will be 0, something like that. And we have a word line horizontally. And here we have 6 transistors. These 6 transistors are required to store the data. In 6 transistors, this P1 D1 making one inverter and P2 D2 making another inverter. And the input of P1 D1 inverter will be connected to the output of P2 D2, and the output of P1 D1 will be connected to the input of P2 D2. It means if we have a output of P1 D1 inverter Q is equal to 0, it means the output of the second inverter will be 1. If this is 1, this will be 0, something like that. So let us understand the read operation. Before going to the read operation, we need to assume that Q will be 0 and Q bar is 1. Means whatever the value of Q, that is what the value we have stored. Now 0 is the value present. We need to read that. So bit is equal to 1, bit bar is equal to 1, we need to set first. Means these two vertical lines, the columns will be having 1. And word line need to be make 1, the next step. When word line is equal to 1, it is giving the voltage to the gate of A1 and A2, it will make A1 and A2 transistor turn on. When A1 and A2 turned on, because of this Q will be having 0, the inverter input will be having 1. Means Q is equal to 0 means the inverter input is 1. That's why it is getting 0. And also you can assume that Q bar will be having the reverse value 1. That will make this inverter input 1. And because of that one, D1 is on. Now the thing is Q is 0 and D1 is on, A1 is on. We'll be having 1 at the bit line. This one will be passed through A1 and it will pass through D1 and it will be connected to ground. What it says? It says bit line is discharging its value to 0. Means we have precharged this bit value to 1. Now after the reading operation, bit will be going to 0, but bit bar B means bit bar will be at 1 itself. It says we are reading the data 0. Suppose if this Q is equal to 1, a Q is equal to 1 in the sense we have stored the value 1 and we are reading now. Again we need to precharge this to 1, bit is equal to 1 and bit bar is equal to 1. Again word line will be 1. Again A1 and A2 turns on. Now the thing is Q is equal to 1 and Q bar B will be 0. We need to read that. And because of A2 is equal to 1, A1 is equal to 1, these two transistors are turned on. There is a discharge path for bit underscore B through A2, D2 and ground. There is no discharge path for bit line since D1 is off. Q will be 1 and the input of this inverter will be 0. P1 transistor will be on, D1 is off. So there is no discharge path over here. It means bit will be in the same value precharged to high. It means we are reading the value 1. Coming to the write operation, it is also a similar case, but the thing is whatever the value we are writing into the RAM need to be passed from bit, and obviously bit bar will be reversed to that. If we are writing 1, bit will be 1 and bit bar will be 0. And then we need to turn on this word line and A1 will be on, A2 will be on. Because of bit is equal to 1, this data will be available for Q. This Q is equal to 1 now, means we are storing 1. Because of that Q is equal to 1 and we are connected that to the input of the second inverter, this inverter output will be 0. And obviously bit B is giving 0 only. And this value will be stored over here since Q is always 1, Q bar will be always 0 since the two inverters are connected in such fashion. So 1 will be stored over here continuously. This is what the write operation is. And with this we will be having some sort of transistor sizes we need to keep, like in order for Q to not flip, D1 should be stronger than A1, means D1 transistor here should be stronger than the A1 transistor and A1 should be stronger than the P1 transistor. So these are the things we need to maintain to get the exact value. And also you can write the sense amplifier with this. You can see in this figure the top one is again the 60 RAM what I have explained here, but the below one is the sense amplifier. This sense amplifier can also be explained. Here the explanation is given since it is asked for the 10 marks. Then we have a choice question in module 3, that is question number 6. Explain the operation of 4x4 NAND based ROM array with necessary circuit diagram. This is the necessary circuit diagram for a 4x4 NAND based ROM. Here since it is 4x4, we need to have 4 rows and 4 columns. R1, R2, R3, R4 corresponding row values, C1, C2, C3, C4 corresponding to column values. Here column values are going to be set depending on the row values. Here the thing is the pull-up transistors are NMOS depletion type transistors. It means if the pull down transistor is off, the output will be set to 1 since always this depletion transistor is on. And if the transistor in the pull down network is having input 1 to the gate, there is a chance of making the output to go low. That is the basic idea here. R1, R2, R3 values are going to be given like this. Accordingly, C1, C2, C3, C4 it is going to generate. Suppose R1 is equal to 0. What happens? This transistor will be off and this transistor will be off. So if this transistor is off, in the sense, in the second C2 we can see this transistor is already off, R1 is on, this transistor is on. Even if this transistor is on, because of R1 is having 0, the C2 will be set to high value. So that is how this logic works. Depending on R1, we need to see what is the other transistor which is responsible for C2. In the first case, while setting C1, only R3 matters. And if you see the C2, how it is generating, because of R1 and R4, if R1 is 0 and R4 is 0, then only C2 will be high. Otherwise it is 0. Similarly, C3, when it is going to set, when R2 is equal to 0 and R4 is equal to 0, it will set. If R2 is 1 and R4 is 1, C3 will come to 0. That is how the C1, C2, C3, C4 values are generated here, depending on R1, R2, R3, R4 values. This is about 4x4 NAND based ROM. And if you want more explanation related to this, you can visit the prescribed textbook in your syllabus, that is CMOS Digital Integrated Circuit Analysis and Design. You will get more information. Then we have a next question. With necessary circuit diagram, explain the operation of NOR flash memory cell with bias conditions. This is the simple NOR flash memory cell. The bias conditions and the configurations of NOR cell is given over here in the table. The different kind of operations we are going to do for a flash memory is that we can erase the memory, we can program the memory, means we can write into the flash, and we can read the data. At that time, these you can see in the diagram, bit line 1, bit line 2 are there. Similarly, we have a source line, and then we have 3 word lines. Since it is 3 rows, that's why 3 lines. Word line 1, word line 2, word line 3. Considering this transistor is the one cell which we have taken for write or read, these are the different values we are supposed to give from the lines. Bit line 1, bit line 2, source line, word line 2, word line 3. So this is the simple explanation which I am giving here. You need to write this as well as this. And for the more explanation, you need to again refer to this book. Erase, programming and read we can do. And while erasing, we need to provide the highest voltage from the source line. It is connected over here. And while programming, we need to give the voltages like this. And while reading the data from the bit line, we are supposed to provide the voltages like this. And for the more information of different biasing methods and the voltage levels and what are all those conventions, you can read this. Here the voltage levels, what is VCC, VSS, chip select, write enable and output enable, and other read operation and write operation, erase operations are going to be done, and some production mechanisms are given here. And then explain the hysteresis characteristics of a ferroelectric capacitor with necessary diagram. The ferroelectric RAM, that is random access memory, here they have asked to write the characteristics. It means hysteresis characteristic says how the polarization of that material changes with respect to the electric field. You can see here in the x-axis we will be having a applied voltage, and in y-axis we will be having a polarization. And these points indicating QS, QR are the different values of the charge. And polarization will be increased when the electric field increases from 0. And polarization will be remain constant when it is at a certain point, and polarization will be decreased as the electric field decreases. That is how the polarization and the electric field will be dependent here with respect to the ferroelectric capacitor is concerned. And also again, for the more information, you need to refer 3rd or 4th edition of that prescribed textbook, so that you will get more information about this. The 4th module question, that is 7A. Differentiate between fault and failure with an example. Explain different types of stuck-at faults with example. First, we need to define what is failure and what is fault. Failure in the sense, in a logical circuit or in the digital system, if the behavior deviates from the specified behavior, we call it as a failure of the system. Means it is not behaving as per our expectation. So fault in the sense, it is a physical defect, like it can be a short circuit, or it can be a open line or open circuit between the two ends of the circuit. We call it as fault. So for example, you can see short between two signal lines in a circuit, or break in the signal line will be called as a physical defect. That can be an example for the fault. And the error will be usually any signal in a circuit may change from 0 to 1. If it is 0 is a correct state, it will be changed to 1 as a non-correct state. We call it as a fault. It may happen like this. So the nature of fault can be classified as a logical or non-logical. Here they ask to explain different types of stuck-cut faults. So there are two types first, logical and non-logical. Logical fault causes the logic value at point in a circuit become opposite to the specified value, as I said here. Non-logical faults indicates rest of the faults such as malfunction of the clock signal, power failure, etc. will be called as non-logical. As the name says, logical in the sense the logic value will be changed, and non-logical in the sense it is not with respect to the logical value. You can also read the explanation over here for more explanation. Let us go to the stuck-cut fault. In stuck-cut fault we have two types. One is stuck-cut 0 and stuck-cut 1. Any node or a output or input node will be stucking to a particular value like 0 or 1. We call it as stuck-cut 0 or stuck-cut 1. Stuck-cut 0, stuck-cut 1 faults are often abbreviated as SA0, SA1 respectively. In the example diagram you can see it is an AND gate with AB inputs and output is Z, but A is stuck at value 1, means whatever the value you give it to A, it will not take that value. This A will be stuck to a value 1. It is connected to maximum voltage, we can say. So this kind of explanation is required for this question. Here they have asked to write the different types of stuck-cut faults and fault and failure you need to explain. Since it is for 5 marks, this much of explanation is sufficient. Then comes a kind of problem. Here for the circuit shown in the figure, using Boolean difference, we need to detect S at 0 means stuck at 0 and stuck at 1 at x2. At x2 they are asked to find, means we need to generate the test pattern, or we can say the combination of input values to detect whether x2 is stuck at 1 and stuck at 0. And also the second thing is determine partial Boolean difference for the path they have given. This path is like from x2 go to L point, this is L point, and then come to N point, then P point, then F. This is the path they have given to determine the partial Boolean difference. So for the given circuit, first we need to find the expression, what you call it as a network function. So this is the network function for the given circuit in the question. So for that easily you can find the network expression by taking the logical gate outputs. And then we need to find the conventional Boolean difference of the output F with respect to the inputs. Here in the question they have asked to find for the x2 node, means to x2 only, but in my explanation I have taken from the prescribed book. Here the example is given for all the nodes. Just look at all the thing, or you can concentrate on x2 for the answer of this question. So we need to find out the Boolean difference for F with respect to x1, in the sense we need to differentiate df by with respect to x1, that is df in the sense that is the output F. We are differentiating with respect to the node which we are treating, that is x1. df by dx1 becomes, in this expression if you see, here we have x1 bar in this part, here also we have x1 bar. So the df by dx1 becomes x2 into x3 bar plus x2 into x2 bar into x3. This is the Boolean difference for F with respect to x1. In the question they have asked to detect S at 0, S at 1 at x2. So we are writing df by dx2 in our answer. It will be x1 bar x3 bar plus x1 bar x3. Similarly for x3 they have given over here. Now by looking at these three, we can write the test values for stuck at 0, stuck at 1 for x1, similarly stuck at 1, stuck at 0 for x2, similarly for x3. How to write? For x1 stuck at 0, to check stuck at 0, what values we need to give from x1, x2, x3 means, see here in the Boolean differences we got an expression x2 x3 bar plus x2 bar x3, means x2 x3 bar in the sense x2 should be 1, x3 bar in the sense in place of x3 it should be 0. x2 1, x3 0. You can see here the first one is x1, second line is x2, third line is x3, x2 into x3 bar. So x2 is 1, x3 bar in the sense it is 0. We are checking whether it is stuck at 0. So in place of x1 we need to put 1 over here. Or the second part, x2 bar into x3 also we can give. x1 will be 1 and x2 bar in the sense it is 0, x3 in the sense it is 1. That is for stuck at 0. For stuck at 1 we need to give x1 as 0 and these values are same with respect to this expression. For x1 I am telling. But here in the question they have asked to detect stuck at 0 and stuck at 1 for x2. Now look at this expression which I am showing with an arrow mark. Here we have x1 bar into x3 bar. It means x1 place we need to have 0, x3 place we need to have 0. So 0 0 we have. In x2 place while detecting 0, stuck at 0 we need to put 1. Similarly the other value also. Here x1 bar into x3 is there. x1 bar in the sense it is 0 again. Yeah, x3 in the sense it is 1, but to detect stuck at 0 we need to put x2 as 1. So to detect stuck at 1 fault we need to give these two will be 0 0, x2 becomes 0. Here these two will be 0 1 like as it is and x2 will be 0. Similarly for x3. So this is how you can write the answer for the first part of this. In the second part they ask to determine partial Boolean difference for this path. So let us see how to find that. So here the partial Boolean difference in the sense as the path is given like this, x2 through L, then N, then P, then F, df by d2, dx2 we need to do. It means df divided by dx2 we are supposed to do, and it is splitted as df by dp and then dp to dn, dn with respect to dl, dl with respect to x2. That is how it will be. So now similarly as we did df by dp in the sense, yeah, what is f here? F is x1 XOR with p. x1 XOR with p in the sense that is x1 plus p whole bar. x1 plus p whole bar can also be written as x1 bar into p. Apply the De Morgan's theorem, then we will be getting x1 bar into p bar for this f and p for the output NOR gate. And if you differentiate with respect to p, the remaining term will be x1 bar. Similarly we need to do for dp by dn. Here this is the p node and this is n node. dp by dn in the sense it is p is XOR of m and n values. So it is m bar into n bar. It will be m plus n whole bar again for p. Apply De Morgan's theorem, it becomes m bar into n bar. So with respect to n we are doing the differentiation, it becomes m bar. So what is m we need to find out, and then m bar will be x2 plus L. L is XOR of x2 and x3. So this is the final expression we got. Similarly dn with respect to dl, dl with respect to dx2, we got all these. Then we need to multiply all these four terms. df divided by dx2 will be this x1 into this term into this term into this term. All four terms we need to multiply. Finally we will be getting this expression. So therefore the test that will exercise the path, this will be, see here x1 bar into x2 into x3 bar, this will be the one of the set, or x2 bar, x1 bar, x3 bar, that can be the set you can say. This is how we need to find the test pattern for the given expression or the path. Then the next question is explain stuck open faults in CMOS circuits with an example. Stuck open paths in the sense it is like, let us see, stuck open transistor implies permanent opening of a connection between the source and drain of the transistor. So the drain source resistance of the stuck open transistor will be higher than the half resistance of non-faulty transistor. Means stuck open fault in the sense something is open, not connected, that is drain to source connection is open. So go through this explanation. There is a supporting explanation over here, and Also with the example, if you see the two input CMOS NOR gate we have considered over here. It requires two N transistors in the pull down, two NP transistors in the pull up. So if we take stuck-at open fault over here for the T2 transistor, suppose we are assuming that this T2 transistor is stuck open. Open in the sense here there is no connection established between source and drain. So if T2 is open circuited, then input AB for AB, if we treat it as 0 0, pull-up circuit will not be active. Why? Because T2 is broken, T1 is on, T2 will not be on. So that is what the problem occurs over here. And then in fact the output remains it as a previous logic state. If the previous logic state is 0, 0 will be the state. It will not be having any path to charge. That is how we need to explain this stuck open faults by taking an example of this kind of example. What is fault diagnosis? Explain one-dimensional path sensitization technique for combinational circuits with an example. The fault detection in the sense it is discovery of something wrong in the digital system or the digital circuit. The fault location means the identification of the fault with components, functional models or subsystems depending on the requirement. Fault diagnosis includes fault detection as well as fault location. Fault detection in the sense in the system we need to detect that the fault has occurred. Fault location in the sense we need to find where actually that is occurred. So you can see this is the example circuit with stuck at one fault. So here for X3 you can see the gate 5 will be having an input called X3. This X3 will be stuck at 1. Taking this as an example, here the clear-cut explanation is given. Please go through this. Here let us consider the circuit and suppose the fault in the line X3 it will be stuck at 1. To test this X3 for set at 1, X5 and X2 must be set at 1 and X3 set at 0. G2 must be set at 1 and X3 must be set at 0. G2 in the sense the output of the NOT gate here. G4 we need to give it as 0 so that G2 output will be 1 and X3 set to 0. We need to test X3 is set at 1 or not, so we are giving X3 as 0 so that the output of this G5 will be 1, right? That is how we need to understand. So carefully go through this. I need to write it in steps because of less time I am not explaining this in detail. Please go through this, you will be understanding how actually this will be so for the one-dimensional path sensitization technique. Then the next thing is find the test pattern for the line 6. Line 6 in the circuit is this as stuck at 0 for the circuit shown in the figure using D algorithm. So the D algorithm will have certain steps, like we need to understand what is singular cover of a logic gate, what is primitive D cube of a gate, and then we need to understand what is propagation D cubes. So and then D intersection. We have 4 steps here. We need to understand all these 4 steps to write this table. So first we need to take this fault node. This fault line is assuming that stuck at 0. So for this, if you write the primitive D cube of a fault line, 6 will be the output of this G2 gate. This G2 gate is a NAND gate. You can see NAND gate truth table here it is. And we need to assume that output D, let us take it as 1 and D bar will be 0. So D will be 1 only when one of the input will be 0. When one of the input is 0, then only the D will be 1. For 1 0 it is D, for 0 1 it is D, and for 1 1 it is D bar. That is the primitive D cube of the faulty path. So then if we consider the next gate, for that we need to call it as a propagation D cube. So now we need to write the propagation D cube for G4. G4 is the next gate where the value will be propagated to G4 through G2. So for G4, while writing the propagation D cube says these combinations indicate that if one of the inputs of the NOR gate is 0,
the output will be complemented of the other input. Means we need to take the set of inputs in that way. So here also for the NOR gate, you can see if one of the input is 0, the output will be complemented to the other. So we need to take these three. So the output will be D bar, D bar, D bar for these three combinations. So next for the G5, if you write the propagation D cube by looking at the change in the one input changes the output, here is this value 0. So that's why for the inputs 1 and D means 1 1, the output will be 0. Then again for 1 1 we need to take, like 7 should be at D, and similarly the propagation D cube for G5 is this. Now by taking these into consideration, we need to select the PDCF, that is primitive D cube for the fault, that is at 6, stuck at 0. So by taking this first one into consideration, 3 is having 1, 4 is 0, 6 is D, 1 0 D. The second step is to intersect with gate 4 with propagation D cube. For this 1 0 D, taking as it is, 3 is 1, 4 is 0 and 6 is D. For that G4 will be having 0 D D bar for 6, 8 and 2. So 2 will be 0 and 6 will be having D as we know, and 8 is D bar. Now intersect with gate 5 propagation D cube. This is the gate 5 propagation D cube with for these values. So here these things will be as it is, and for that 7 will be having value 1 and 9 will be D bar. So 9 is D bar because of 8 is having D. 7 is 1 and 8 is D. 9 will be D bar. But here we will be having a combination of 7, 8 as 1 and D bar. 1 and D bar for the NAND gate becomes, the output will be complemented to this. That's why it becomes D. Now, so then we need to look at the other values, other lines like 7 as well as 5. By looking at G3 singular cover and G1 singular cover, we need to put the values for line number 5 as well as line number 1. So this becomes the pattern to detect the stuck at 0 at particular line 6. So this is how, if they ask you to find the pattern, test pattern for any of the other lines, we need to do all these procedure to find out the test pattern. This should be the test pattern now. By using this, we can find out the stuck at fault at 6. So this is about module 4. You need to understand this D algorithm clearly to get the exact test pattern for the stuck value of any particular line. So if you do any small mistake while taking the values, the final test pattern will be wrong. So carefully you need to write these values for the singular cover, primitive D cube as well as propagation D cube, so that you will get the exact test pattern. For the state table shown, find the response for 101 sequence, harming tree and distinguishing tree. Here the present state is given ABCD, and input x is equal to 0, x is equal to 1 is given, and their outputs are shown. So we need to write the sequence here. For 101 sequence, we need to write the response, harming tree and also the distinguishing tree. No much explanation is shown over here. Please refer the prescribed textbook for this, for getting the more information. This is the brief answer which is required for this question. Please write the explanation also by reading through the textbook. Explain the various phases involved in checking experiment based on sequential circuit structure. There are three main phases. Initialization phase. During this phase, machine under test is taken from an unknown state to a fixed state. That is what initialization phase is. All the sequential circuits will start with the reset phase. We are going to reset, and then we are going to power up and then initialize. So that is what the very first phase over here. And then we will be having a state identification phase. It will be in input sequence is applied, so as cause the machine to visit each of its states and display its response to the distinguishing sequence. And then we have transition verification phase. At this phase, machine is made to go through every state transition. Each state transition is checked by using the distinguishing sequence. These are the three stages or phases, we can say, checking experiment based on sequential circuit structure. Then explain the process of testing sequential circuit as iterative combinational circuit. You can see the sequential circuit block diagram first at the top. And the next one is the iterative model of sequential network. Iterative model of sequential network says it will be connected back to back, means one after the other, n number of combinational circuit with an flip-flop, making the sequential circuits can be connected. You can go through the explanation which I have given here. It gives you the clear-cut idea on the process. Then define the terms controllability and observability with example. These two concepts, controllability and observability, are very important in analyzing doing the tests using test patterns. Controllability refers to ability to apply the input patterns to the sub-circuit via primary inputs of the circuit. Example is given in 5.1. Here it shows the controllability. And observability refers to the ability to observe the response from the sub-circuit via primary outputs of the circuit. So for more explanation, again you need to go through the textbook and find the more answers if it is asked for more marks. And the next question is, with the neat logic diagram, explain the clocked hazard-free latches used in LSST technique. So here is the answer for that. You can see the hazard-free polarity hold latch here, that schematic, as well as flow table and excitation table for that, and also the logical circuit they have given, and also polarity hold shift register latch and logic for shift register latch is also shown over here. So the next question is, explain any two ad hoc design rules for improving testability. There are multiple rules. There are many ad hoc design rules are there for improving the testability. Here they have asked you to write two such rules. So you can go through all the rules, better to know. If they ask for 10 to 12 marks, you need to write all the rules in your answer. So you can write two ad hoc design rules in this question. You can go through this. This is the answer for that particular question. So this is the end of the solution for model question paper for the subject VLSI design and testing.